Imagine a freezing winter morning. You reach for a metal doorknob, and it sends a shiver up your spine, feeling like pure ice. Then, your hand glides to the wooden banister beside it, which feels merely cool, almost temperate. An undeniable difference, right? You'd swear the metal is far, far colder than the wood. But what if I told you that, at that exact moment, those two objects were, in reality, the exact same temperature? Yes, you heard that correctly. The frigid doorknob and the cool banister, both sitting in the same room for hours, have reached what scientists call thermal equilibrium with their surroundings. They are, thermodynamically speaking, identical in temperature. This isn't a trick of the light, it's a fundamental trick of perception, a daily illusion our own bodies play on us, misinterpreting a basic scientific principle. Your senses, the very tools you use to understand the world, are lying to you, and understanding why they lie will fundamentally change how you perceive everything, from a hot cup of coffee to the very fabric of the universe. What crucial piece of information are our brains missing that creates this widespread, deeply ingrained misconception? So, if temperature isn't the culprit, then what is? The answer lies in a phenomenon called thermal conductivity. Think of temperature as a measure of the average kinetic energy of the particles within an object, how much they're wiggling and jiggling. Heat, on the other hand, is the transfer of that energy from a warmer object to a cooler one. When your skin, which is typically around 33 degrees Celsius or 91 degrees Fahrenheit, touches an object at room temperature, say 20 degrees Celsius or 68 degrees Fahrenheit, your body is always the warmer object. Heat will flow from your hand to the object. The question is, how fast? Imagine heat as water in a pipe. Some pipes are wide, smooth, and unobstructed, superhighway for water. Others are narrow, winding, and filled with gravel, a slow, torturous dirt track. This is precisely the difference between metal and wood. At a molecular level, metals like aluminum, copper, or steel are fantastic thermal conductors because of their unique atomic structure. They have what are called free electrons. These electrons aren't tied to specific atoms. They're like a bustling crowd, able to move freely throughout the material. When heat energy, which is essentially atomic vibrations, enters a metal, these free electrons grab that energy and zip through the material, rapidly transferring it from one atom to the next. They are the express delivery service for heat. Wood, on the other hand, is an organic material made primarily of cellulose fibers. Its electrons are tightly bound to individual atoms and molecules, locked into place. There are number-free electrons to act as heat couriers. So, when heat energy tries to move through wood, it has to rely on a much slower, more inefficient process. Atom-to-atom vibration. Imagine trying to pass a message through a crowded room by whispering it from person to person compared to shouting it through a megaphone. That's the difference. Wood is an insulator, a thermal bottleneck. When your warm hand touches that room temperature metal doorknob, the metal's free electrons immediately go to work, efficiently siphoning heat away from your skin, carrying it deep into the doorknob. Your skin's temperature receptors register this rapid, drastic loss of energy, interpreting it as cold. It's not that the metal is colder, it's that it's a super efficient heat thief. When your hand touches the wooden banister, however, the wood's poor conductivity means it can only steal heat from your skin very slowly. The rate of heat transfer is low, so your receptors don't register the same. Dramatic drop in skin temperature. It feels less cold, perhaps even neutral, because your body isn't being rapidly drained of its warmth. The paradox begins to unravel. Our sensation of cold isn't an absolute measure of an object's temperature, but rather our body's perception of the rate of heat leaving us. This is a crucial distinction that most people miss, and it rewrites how we understand our interaction with the physical world. But this fundamental principle of heat transfer has far more mind-bending implications than just a doorknob. If the cold sensation is merely a rapid drain of your body heat, consider this counterintuitive thought experiment. What if both the metal and the wood were hotter than your body? Imagine touching a metal baking sheet fresh out of a 200 degrees Celsius oven versus a wooden spoon that's been stirring a pot on the same stove. The metal sheet would instantly cause a severe burn, while the wooden spoon, though hot, might be manageable to touch for a brief moment, causing less immediate damage. Why? The same principle, just in reverse. The highly conductive metal rapidly transfers heat to your hand, causing rapid tissue damage. The insulating wood transfers heat much slower, giving you a precious extra second to react. It's not just about stealing heat, it's about the speed of that energy exchange in any direction. This leads us to the biggest payoff, the ultimate revelation that truly flips our understanding. The sensation of cold is not an inherent property of an object. Objects don't contain cold. They contain heat energy, or they lack it relative to another object. Cold is a purely subjective, human experience. It's the sensation of your body rapidly losing its internal thermal energy to its surroundings. Your skin's thermoreceptors aren't thermometers. They're rate of change detectors. They are finely tuned to detect the flux of heat, not the static temperature of what you're touching. This is why if you hold an object long enough, even metal, it will eventually feel less cold as the surface layer of your skin cools down and the rate of heat transfer decreases. You are, in essence, reaching a localized thermal equilibrium with that immediate surface. This profound understanding of thermal conductivity isn't just an interesting parlor trick or a scientific curiosity. It's a cornerstone of modern engineering and design, shaping our lives in countless unseen ways. From the moment you brew your morning coffee to the complex systems keeping astronauts alive, in the vacuum of space, this principle is at work. Think about your kitchen. The bottom of a stainless steel pot is designed to be highly conductive, quickly transferring heat from the stovetop to your food. But the handle? Often made of wood, plastic, or silicone. Excellent insulators, precisely because you don't want heat rapidly flowing into your hand. Or consider a simple thermos flask. It keeps your coffee hot and your water cold by minimizing heat transfer using a vacuum layer. As an ultimate insulator, preventing both conduction and convection. Perhaps the most dramatic applications are found in extreme environments. NASA's Apollo missions and later the space shuttle faced the harrowing challenge of atmospheric re-entry, where temperatures outside the spacecraft could reach thousands of degrees Celsius. How did they protect the astronauts and the integrity of the vehicle? With ablative heat shields and specialized ceramic tiles, materials designed not just to withstand extreme temperatures, but crucially, to be incredibly poor thermal conductors. The space shuttle's iconic white tiles, for instance, could be glowing red hot on the outside, yet cool enough to touch, with bare hands just moments after landing, because the heat simply couldn't conduct through them fast enough to transfer to the interior or to a person's touch. So the next time you encounter that seemingly frigid metal surface or a warm wooden one, remember this: they aren't inherently different in temperature. It's merely a rapid exchange of energy, a silent conversation between objects, where your body is always listening for how fast its warmth is being stolen or shared. Our perception of cold isn't a property of the world, but a dynamic story of heat constantly flowing, constantly shaping our experience. What other everyday illusions, driven by hidden scientific principles, do you think are still fooling our senses?